Singular reinforced beam. So what is our singular reinforced beam? Singular reinforced beams are beams which is only provided with longitudinal reinforcement in the tension zone. So the compressive force is handled by the concrete section only. So for example, we have a beam. So this is our beam. Let's say this is our beam with a width of B and a height of H. So when your beam, having a beam simply supported, let's say that your beam is loaded uniformly. So let us take this section. For example, we take this section and this section appears like this. So we are taking the section within the midspan of the beam. And at the midspan of the beam, your reinforcement is located at the bottom of our beam. So your reinforcement is expressed as AS. And it is at a distance D from the uppermost fiber of your beam. So again, this is at the midspan. So as you can see, because we have a positive moment at the midspan and we have a negative moment at the supports. So when your supports when your moment at the support is negative, your reinforcement is located at the reverse side or at the upper side. We say that your compressive force is handled by your concrete because as we all know, your concrete is a good resistance of compression and your reinforcement is for tension. However, we are not allowed to have a beam like this with reinforcements, let's say, and stirrups. Of course, we have stirrups, but we are not allowed to have beams without upper or other bars in the compression. So our code says that we are required to put at least two compression reinforcement. Yan. This is to hold your stirrups. That is one of the purpose of your compression reinforcement. But it is not necessarily supporting compression. So when you require compression steel bars, when you require this, it is a different matter na, and we will call it a double reinforced beam. So with the positive means moment, if your beam is a simply supported one, you have your positive moment, your moment is positive at the midspan, and the positive moment is creating or has the tension zone at the bottom. So at the bottom yung tension natin, as you can see here, this is the midspan section. And at the midspan section, your moment is positive. So your enforcement that will resist your tensile forces is located at the bottom. In this case, in this figure, you have four 25 millimeter diameter bars that will resist tensile forces. And then at the negative support or the negative moment, which I told a while ago, that your negative moment is located at the supports, your tension zone is at the top. Yeah, always remember that. And with the case of cantilever beams, so you know that the cantilever beams are beams that are supported on one side only. For example, this is our cantilever beam. So if it's supported on one side only, you only have your negative moment, which is the moment at the support. And we assume that the moment at the ends is zero. So so the reinforcement for cantilever beam is always located at the top. So this is the elements of a singly reinforced beam. Okay, again, even though we are placing compression reinforcements, even though we are placing that, we are still considering that your tensile force is only at one side. Nasa tension zone lang. So that is your AS. So that AS is measured from the midspan or from the middle of the bars to the uppermost fiber. Yan. That is your D. So actually you will have another figure for this for the moment diagram, that it is not literally go looks like this one. It is not literally a rectangular compressive block. Somehow it's like this one. Medyo may changes pa siyang ganyan. Yan. Yan pa yung compression block natin eh. Kaya lang, for a easier way of computing it, nireduce na natin siya into like this. So, but before that, we have the stress and strain relationship of the strain. This is the strain of steel, and this is the strain of concrete. So that is the strain. Then you have your compression block. So the width of your compression block is 0.5 F prime of C, and the height is A, which is equal to beta 1 of C. And your tensile force is equal to your area of steel multiplied to your yield stress, or the stress of your steel. So these are the minimum code requirements. For our beam, of course, we have some requirements. Like for example, this one. So when you are having your beams, of course, hindi naman yan exact na stirrups, tapos reinforcement, and then cement. So we have your environmental covering so that the water does not penetrate easily our concrete. And of course, we all know water is not good for our steel because it may oxidize our steel and deteriorate our steel. So we are having concrete coverings, and that concrete coverings are that is measured from the outermost layer or outermost fiber of the concrete to the outermost layer or fiber of your steel stirrups. So that is your concrete covering. So for external beams, so that is your beams exposed to weather, we are using 50 millimeters, and for internal beams is 40. So if the beam is not stated whether it is exposed or not to weather, you are safe to use 40 or even 50. So this, of course, as a designer, as an engineer, you are the one to decide which concrete covering are you going to use. And of course, that the fact of having it economically is one of the duty of an engineer. So concrete covering is the concrete coating from the stirrups to the outermost area of the beam. Then in designing the compressive strength of concrete, so we all know that on the compression block, it is one of the most important element is your F prime of C. So in RCD, we will always encounter F prime of C because this is the compressive strength of concrete. And the compressive strength of concrete depends on the type of mixture. So I know you are only familiar with class A and class double A, but in structural engineering, there class triple A and quadruple A, 4A or 4A do exist. So in materials engineering, you already encounter your class A, which is 20.7 megapascals, and class double A is 27.6. So we still have class B, diba? Class B and class C. However, we are not considering B and C as concrete mixture for structural members. Yeah. We can use this as pavements for plant box, but not for structural. The minimum mixture or compressive strength that you can use in structures is class A. Of course, we do want to have a safe and with a durable structure. So triple A do exist and 4A do exist. So yeah, in having we have equivalent mixtures for this. I think class A has 9 bags, zero point 0.5 cubic meter of sand, and 1 cubic meter of gravel. Then for double A, I think it's 12, if I'm not mistaken. So it's easy to remember the equivalent megapascal or the equivalent number in compressive strength in MPa of the class. So as you can see, we can round this off as 21. This is 28. This is 35. And this is 42. So as you can see, there's only an increment of 7 for every change of class. So it has something to do with your beta 1. Later on, you will appreciate that increment of 7. So of course, if we do have standards for your F prime of C, we also do have standards for your steel bars, which is designated by your FY. So we do have FY in MPA and FY in KSI. So your steel bars, you in the market, you will not say that you are requiring 24 to 248 megapascals. Unlike in concrete, what you are going to do is that you tell for example, you are ordering to the batching plant or mixing for a mixing job. You will instruct them to give you 20.7 megapascal of concrete, and it's already mixed in you what the concrete that will be given to you is what you specified. But in steel bars, we are not using megapascal to specify our orders. Instead, we are giving the grade of steel. So it is quite obvious that the grade of steel is also equal to your KSI. You can see. So grade 40 has 40 KSI, grade 50 has 50 KSI, grade 60 has 60 KSI. So it's easy to remember what is the equivalent tensile strength of a steel bar depending on the grade. So you just have to convert KSI to megapascal. I think 1 KSI is equivalent to 6.9 megapascals. So you always take note of that conversions. So yeah. So in designing our beams, we have 3 modes of design. We have the balanced design, the over design, and of course the under design. So the 3 modes, yung 3 modes na meron tayo in designing, we have the balance, under, and over design. So let's see which is the best to use. So with the balanced design, we are assuming that your Fy is equal to your Fs. Fs is the actual, and yung Fy natin is the yielding capacity of steel, When we say yielding capacity, this is the point where your steel is at the point of having its rupture, near to its rupture, or it will suddenly broke, if it will go into failure. So by the way, the formula for Fs is 600 times your depth, minus C, which is equal to A over your beta 1 over C. So if your Fy, or this is a property of steel ha, this is a steel property. So given na to lagi. This is a steel property. If the steel property or the Fy is equal to your computed Fs, the actual stress given by the steel. So if it's equal, then your design is balanced. Then on the other hand, if your Fs is greater than Fy, that is under. And then where your Fy is greater than your Fs, so therefore that is over design. Because it means that the steel that you placed on your concrete has a greater reinforcement or a greater strength than what it is actually giving to the concrete. Okay, so now, which of the three is best for us? Okay, I will give you a scenario of an earthquake. So this, for you to easily imagine what happens with this different mode of design. So I will tell you this. So during the balance design, what happens is that when you have an earthquake, then let's assume that the earthquake experienced by the structure is really stronger than the designed earthquake that it can resist. So definitely the structure will fail. Let's say when your design is balanced, since your steel is yielding, will yield at the same time. So when your concrete fails, your steel reinforcement also fails. So for example, the building will collapse. It will collapse all of a sudden because concrete and steel are both failing. Okay. So definitely we do not want a sudden collapse. So with the under reinforced, steel reinforcement inside our concrete fails first before your concrete. And over design, when we are using over design, definitely during tough times, your concrete will fail. Concrete is failing, so you can observe falling debris already. But still, since your steel is not yielding yet, your steel remains firm. So for example, pwedeng nag-collapse na all of your concrete materials, but your steel framing is still present. So which is better? Which is the best? Okay. Most of you will think that over design, because it's over design, it is more than of the required. Yeah, that's the word. It is more than the required. However, what's best for our design is still your under design. Okay, why it is under design? Under design is better. Why? Because it do gives our occupants to have a time to evacuate the area. Why do I say so? Because when you're still inside your concrete, for example, this is your beam. And so of course, the steel is inside. This is your steel. So when your steel is yielding, for example, nagkakaroon na ng cracking, nababali na yung mga steel natin. What would happen to the concrete? As concrete will induce both compression and tension at the same time, it will produce cracking before it will totally collapse. So that when you observe that cracking as an occupant, you will know to yourself that you have to evacuate the building. And what we must consider is that when this scenario happens, we have to clear the building so that there's no casualties. So that's what we want. Though we are not saying that okay lang pala na hindi matibay yung building basta nakakapag-evacuate yung mga tao bago mag-collapse yung building. That is not what I'm trying to say. What I'm trying to say is that it is best to have a good building that will never fail. But if circumstances come, at least we gave our occupants to leave the building and put themselves into a safer place. So that's why we are considering under design concretes, reinforced concretes. So this is how we solve your singly reinforced beam. So there's two way of designing or computing for the design of beams. First one is that you are designing the dimensions. What would be the B, what would be the D or the height, then what is your AS. So that is design. And the other one is that you are given tayo nito, this is given. And the question is it safe or not? So there's a two phase of solving the problem. It can be designing, you design the dimensions, the number of bars, or you investigate whether the design is safe or not. So this one. So I'll give you easy steps for you to understand. So of course, we will solve first for the maximum still area. We are solving for the maximum still area so that we know if or we can verify whether your solution should be a singly or a doubly reinforced. So of course now we know that all of our solution is about singly reinforced. But what if it is not stated in the problem anymore? So first, of course, we investigate whether our beam is a singly reinforced or a doubly reinforced by having your maximum still ratio. So the maximum still ratio is solved as the 75% of your maximum still ratio is 75% of your balance still ratio. And this is the formula for the balance still ratio. That is 0.85 of the compressive strength of steel multiplied to your beta 1 times 600 over Fy multiplied to 600 plus Fy. And that would give us the formula of your maximum still ratio. So that is the formula of your maximum still ratio. Okay? So now we have this. In solving your maximum still ratio, again, F prime of C is a property of your concrete. Fy is also a property of concrete. What remains unknown to us is your 0.80, your beta 1. Beta 1, if your F prime of C is less than or equal to 30, it is safe to assume that your beta 1 is 0.85. However, if your F prime of C is greater than, so it's greater than 30, you will solve your beta 1 as 0.85. Of course, since it is increasing, you will decrease every increase from 30 megapascal, you will subtract 0.05. Yeah, this is what I'm trying to say a while ago, this increment of 7, because we are changing your class of mixture on an increment of 7. So for every 7, you have a decrease in beta 1 of 0.05. Sa bawat 7 na increment, magbabawas ka ng 0.05. So, hindi naman laging 37 to, 42. So, sometimes it's 31, 32. So, we are solving that. That is f prime of c minus 30 times 0.05 over 7. That we will less it to 0.85 in order for us to have your beta 1. Then we will solve for the maximum moment. Yeah, a while ago we solved for since it's maximum, every value is at maximum. So this is also your raw max. Fy is given. So we will have your omega. Then we solve for your F. By the way, this is a formula for all ultimate moment, whether it is maximum or not. So that is your phi, reduction factor, which is dependent on what type of code you are using. Let's say in our code, this is 0.9. F prime of c is given. Omega is this. Your base or the width of the beam may be given and maybe not. Your depth, yan, multiplied to 1 minus 0.59 of omega. Okay, so this is how you investigate your moment. So we will compare this mu max to your actual mu, which is coming from the loads of the beam. Whether it is a uniformly loaded beam with a concentrated beam. So I assume that you already know how to compete for the moment, because that is really important to compete for the moment and of course for the reactions. So if you already know the moment, what is the moment, you can compare your actual mu to your maximum mu. So if mu is less than, or your actual is less than or equal to mu max, so if your mu max is, if your mu is less than or equal to mu max, mas malaki yung maximum. And that's what should we expect, that the maximum is greater than your actual, because that's the maximum. It is a singly reinforced. We are positive for a singly. Pag in case, this is singly. But if the actual moment is less than or greater than, than your mu max, mas mataas si actual, then we need to support our beam with the compression side because it's a doubly reinforced beam already. Okay, after knowing if your beam is a singly or a doubly reinforced beam, you will solve for your RU by having the formula of your actual moment. We will use your actual moment here, the moment which is solved from the load of the beam. So from the load to. So we will solve for the RU. That is your phi times your BD. Okay, as you can see on the previous slide, that is also your mu is equal to your phi. F prime of c omega times b d squared times 1 minus 0.59 omega. As you can see on the next slide, diba? We have phi RUBD. So we have your phi. It is also equal BD squared. So you can see that this one and this one is your RU. That your RU is equal to F prime of C omega times 1 minus 0.59 of your omega. I hope you could clearly understand my writing. Okay, so you'll solve for your RU. Then you will solve for the actual still ratio. And this is your formula for the actual still ratio. That is 0.85 of your F prime of C over Fy multiplied to 1 minus the square root of 1 minus 2 of Ru minus 0.85 of F prime of C. And you will solve for your actual still ratio. And that actual still ratio will be used in solving your actual still area. Okay, so the ratio, of course, that is the ratio. That is the ratio of the still area to the area of the concrete. Okay, that is why it is called a still ratio. The area of steel to the area of concrete. So, manipulating this equation, you will have this one. Okay, how about if we are okay? So this one, you can look this one. This is the explanation of the diagram. You can also do this method. And I think this is easier. Yan. As you can see, this is your compression block. Not most of the area, not all of the area of our concrete is considered to resist compression. So this block only, we consider this what resists compression. So kinukuha natin yung gitna, that is your compressive force, that your C. And your C, kasi block nga to, so dapat ganyan siya, di ba? Compression block. Yeah. So ito yung B. This is your B. That is the width of the beam. Then yung A, this is A. That is your AB eh. This is your AB. And yung thickness ng compression block is 0.85 F prime C. Kaya siya naging yung compression natin is equal to 0.85 F prime of C equals to your AB. Sorry, AB. Then it has an equivalent, of course, in the rule of mechanics, it always has to be equilibrium. So the equivalent force is your tension, which is solved by AS multiplied to your Fy. Then your ultimate moment or the actual moment is equal to this is your phi, reduction factor phi, which is 0.9 multiplied to your nominal moment. When we say nominal, there is no multiplier multiplied into it. That's it. So when we take your moment at the tensile side, for example, we have the moment at the tensile. So, syempre, di ba, since this is at equilibrium, we can have summation of moment at the tensile, taking positive moment, clockwise equal to 0, like that. So, you will have this one. Yan, moment ka dito. So, we will have your compression or your nominal moment is equal to your compression multiplied to D. Kasi yung buo na to kasi D eh. Diba? Yung buo na to from your upper compression fiber to your location of your tension, that is simply D. And then the height of your compression block, that is A. Then you are placing your compression force, this is one, from the midspan of your A, so that it would be A over 2. So that is A over 2. So when we have your moment at tension, your moment arm would be D minus A over 2. I hope you do get it. So where in your compression is equal to this one. This is the value of your compression. Therefore, your nominal moment, again, this is nominal ha. Nominal moment in terms of compression is 0.85 F prime of C AB multiplied to the moment arm of D minus A over 2. Over 2. Okay, how about if we take the moment at the compression side, dito tayo mag-moment. Okay, I'll clear it para mas madali. Okay, how about we have your moment at the compression side. We do your moment here. So your nominal moment, again, from your tension to the uppermost fiber of the compression is your depth. Then this is A, the height of the compression block. Then yung compression natin is located halfway. So that is A over 2. So pag nag-moment tayo at the compression side, we will have your nominal moment as your tension multiplied to your depth minus, this is, yung matitira. That is your depth minus your A over 2. Minus A over 2. So then, nominal moment is AS Fy D minus A over 2. Again, this is nominal. Your moments due to your load is your ultimate. And that your ultimate moment is your phi multiplied to your Mn. Okay? So, in designing the reinforcements, we have your moment already. So, you will choose which is more useful if your moment at the compression or moment at the tension. Well, definitely, kasi di ba meron tayong two choices of moments. Two choices of moments tayo, di ba? Yung AS, Fy, D minus A over 2, and we also have 0.85 F prime of C, AB, D minus A over 2. Definitely, and when we are designing for the reinforcement, this is AS. So we can no longer use this formula because AS is unknown. So what is available for us is the compression fiber. So that in here, given tayo ng moment, given to, with MU, given. So, given tayo ng F prime of C, B can also be given also the depth. So, what we are left unknown to us is your A. So, from that, you will solve the value of A. Okay, actually, you will solve for the value of A. Yeah, you could solve for the value of A. And then, using this formula, you can solve for the value of AS. Again, this formula is tension equal to compression. As I said a while ago, that we always maintain the state of equilibrium. We assume that your tensile force shall be equal with your applied compression force. So that is it. Pero before we arrive in solving your AS, we have also to examine your A. And for examining your A, we will check whether it is correct. Kasi it is safe for us to assume that your Fy See, with this, before we solve this, we will examine if it's safe for us to use Fy. Yung Fy na stated with the description of your steel na ginamit natin. Kung yung grade 40 ba, yun na yung gagamitin natin or not. So, if that, so we will examine if your steel is yielding. So, dapat, para masabi natin steel is yielding, yung Fs na ma-solve natin is greater than Fy. Yung strength talaga ng steel na ginamit natin. So, for that, yeah. Okay, kasi nga under design yung kino-consider natin. So, we need C. Ang meron tayo a while ago is A. This is the formula how we could get A. That is C, A over beta 1. So, that's it. If Fs is greater than Fy, then it's yielding. Then we can proceed. If not, Fs is not greater than Fy, then we cannot proceed at all. For investigating whether the beam is safe, for analyzing it is the first step for us is to solve for your A. Because again, the main goal of this is to know what is your maximum allowable moment. Maximum allowable, ha? What is your, sorry, okay, iba kasing MU max eh. MU allowable. Ano ba yung allowable talaga? Then we will compare it to your actual loaded MU. Then if the allowable is greater than the actual, then it is safe. Or we can also do this in order for us to say what is the capacity of a building. Okay. So first thing is we must know the value of A. Again, that we are taking the tension is equal to compression, so that ASFY is equal to 0.85 F prime of CAB. So we can have your A. As easy as that. Wherein your AB, yung AS natin ha, yung AS natin can also be solved if not given particularly. This is the number of bars multiplied to the area of one bar. Okay. Then, when we solve for A, we will solve for your Fs to test whether your steel is yielding or not. So, if Fs is greater than Fy or equal, then it is yielding. Okay, what if it is not yielding? What if Fy is greater than Fs? What you will do is you go back in here in this formula and replace Fy with the formula of Fs. Formula of Fs, not Fs, the value of the Fs you solve, hindi ito. Instead, you will replace it with 600 times D minus C over C. Ito yung re-replace nyo sa Fy. But you can have two unknowns. Your C and A is unknown. However, you have the relationship between A and C. Diba? With the use of your beta. So, babalik kayo doon, then you will solve the real value of A. And after that, you will solve for the moment. So, you can solve for the moment at tension, or moment using compression, moment using tension. And it shall be equal. For you to check din pala kung tama yung ginagawa nyo, dapat equal ang moment due to compression and moment due to tension. Then, that is a nominal. Then, kunin nyo lang yung ultimate by multiplying your reduction factor, which is 0.9.